Hello and welcome back to part 2 of this video series documenting my project to develop a Raspberry Pi Pico driven sensor to detect pollinators, in particular bees, through audio classification. I was on holiday recently and next to the cottage where I stayed was this magnificent horse chestnut tree in full flower at the time. All day and evening it was humming with bumblebees and other insects. It was wonderful to watch, and I wish I could go back there to test the sensor when I'm ready, as I've never seen so many bees in one place before. Today I wanted to share with you some progress I've made with the project. I don't have much video of the sensor hardware yet, which although it has all been ordered, it has not all been delivered. So instead, here's some more videos of flowers to help us get into a bee-like frame of mind. Let's talk about solar panels first of all. Now, I live in the UK, a country of course internationally famous for our all-year-round intense sunlight and cloudless skies. But somehow, when I began looking up sunlight data to feed into the calculations, I was a bit disappointed to find that in December, for instance, the UK receives on average just 1.7 hours of sunlight per day, rising to only 3.6 in March. Luckily, according to the Woodland Trust, most bees hibernate between autumn and spring, waking up in around March. So to avoid hugely increasing the cost and size of the system for relatively little gain, I've decided to design it purely for March to September operation. Summing up my components, and assuming the transmitter will only be actively transmitting for 10 seconds every 5 minutes, I believe I need a constant 0.3 watts to run the sensor. Thrashing through the calculations then, with some factors to take a pessimistic view of how much sunlight we'll get, and the efficiency of the panel, and I believe a 3-watt panel will provide sufficient margin, when paired with a 3000 mAh 3.7 volt Li-ion battery. I also need to choose a transceiver, which will be used to send the detection data back from the Pi Pico-based sensors to the base station, a Raspberry Pi 4. There are a bunch of different off-the-shelf breakout boards. Many of these use 2.4 GHz, but I chose the HC12, running between 433 and 473 MHz, as that is apparently a better frequency more suited to use in outdoor spaces, where 2.4 GHz signals can get absorbed by wet leaves and vegetation more easily. The HC12 is also well supported by Raspberry Pi, so it should be fairly easy to implement. Now the HC12 can achieve nearly 2 kilometers of range, at 100 milliwatts transmission power. Which sounds great, I thought. Let's just go to the regulations, that's IR 2030 in the UK, and check that this is compliant. And oh wait, this is in fact illegal, both in terms of power and actually the frequencies that the HC12 can transmit at. It's probably a common mistake to make, given that anyone can buy one of these on eBay for a few quid, plug it in, and not realise that they're actually breaking the law. There are, however, luckily some program-side settings that we can use to both limit the output power and also limit the frequency to within legal boundaries. With a legal power setting and the default spring antenna, I should be able to achieve 180 meters of range from data I found on the internet, and by using a different antenna that can be increased. I think this will do. Apart from that, I've been enjoying some concept sketching, and also playing more on Google Colab with the audio classifier training process. I'll do a dedicated video on this soon. Thank you for watching. See you again.